In this problem, our objective is to return the values of the nodes of a binary tree that are visible from the right side, ordered from top to bottom. The right-hand view consists of the nodes visible when looking at the tree from the right. This problem can be solved efficiently using a depth-first search approach, which helps us capture the rightmost nodes at each level of the tree. To achieve the desired right-side view, we need to systematically traverse the tree, keeping track of the depth of each node and adding the first node encountered at each depth to our output. By prioritizing the right child during the DFS traversal, we ensure that the rightmost nodes are processed first, which guarantees that the right-side view is accurate. Each node in a binary tree is defined by a three-node structure. The structure contains an integer value and pointers to its left and right children. The function rightSideView takes the root of the binary tree as a parameter and returns a vector of integers representing the right side view of the tree. Inside this function, we declare a response vector that will store the rightmost nodes at each level. To perform the DFS traversal, we define a DFS lambda function inside the right side view. This DFS function takes two parameters, a pointer to a tree node, the current node, and an integer representing the current depth. The DFS function is designed to explore the rightmost subtree first, ensuring that the rightmost nodes are encountered before the leftmost nodes at each depth. Within the DFS function, the first step is to check if the current node is null. If it is, we simply exit the function as there is nothing to process. Next, we check if the current depth is equal to the size of the response vector. If it is, it means that we have reached a new depth level, so we add the value of the current node to the response vector. Then, we recursively call the DFS function on the right child of the current node, incrementing the depth by 1. After that, we call the DFS function on the left child of the current node with the same incremented depth. This traversal order ensures that the rightmost nodes are prioritized. After defining the DFS function, we call it with the root node and an initial depth of 0 to start the traversal. Finally, we return the response vector, which contains the values of the rightmost nodes at each level of the tree. The systematic approach of tracking the depth and prioritizing the right children ensures that our solution is both time efficient and accurate. To illustrate how this algorithm works, consider a binary tree with the following structure. In this tree, the nodes visible from the right side are 1, 3, 6, and 7. Here's how the algorithm processes this tree step by step. We start with the root node, which is 1, at depth 0. Since depth 0 is equal to the size of the response vector, which is initially empty, we add 1 to the response vector. We then move to the right child of node 1, which is node 3 at depth 1. Since depth 1 is equal to the size of the response vector, which is now 1, we add 3 to the response vector. Next, we move to the right child of node 3, which is node 6 at depth 2. Since depth 2 is equal to the size of the response vector, which is now 2, we add 6 to the response vector. We then move to the right child of node 6, which is node 7 at depth 3. Since depth 3 is equal to the size of the response vector, which is now 3, we add 7 to the response vector. Node 7 has no children, so we backtrack to node 6 and check its left child, but node 6 has no left child. We continue backtracking to node 3 and check its left child, but node 3 has no left child either. Finally, we backtrack to the root node 1 and check its left child, which is node 2. Node 2 is at depth 1, but since depth 1 is already represented in the response vector, we do not add node 2. We then check the right and left children of node 2, nodes 4 and 5 respectively, but since the respective depths 2 and 2 are already represented in the response vector, we do not add them either. Thus, the final response vector is 1, 3, 6, 7. which correctly represents the nodes visible from the right side of the tree. Our solution involves systematically traversing the tree while keeping track of the depth of each node. By adding the first node encountered at each depth to the result vector and prioritizing the rightmost child during DFS traversal, we ensure the rightmost nodes are processed first. This approach is both complexity efficient and correct, allowing us to handle large-sized inputs in a reasonable amount of time. Now, let's test this algorithm to make sure it works. Remember, there are many ways to implement an algorithm, and trying out different ideas is always a good practice.